So the first thing I noticed from Tuesday's Jamboard is that some people had difficulty sorting linear versus nonlinear equations. It's important to remember that a linear equation is going to form a line, and a nonlinear equation will form a not line, or something curved or bent, something like that. And if you remember from before vacation, we did a little activity on this where we entered all these equations into Desmos, and we saw which ones formed lines and which one didn't. What we saw then is that if x had an exponent that was bigger than 1, that it was going to be nonlinear. So right away, that would mean that like x squared would be nonlinear, 4x squared plus 1 would be nonlinear. This one here, x squared plus 3x plus 1 would be nonlinear. And then if I look at all of these other equations where I've got just x all by itself, even though this one has a fraction, all of these are going to be linear. And the reason these are linear is because in all of these cases, the highest exponent of x is 1. So it doesn't matter what comes in front of x at that point, it just matters that the exponent of x, even though it's invisible, is an exponent of 1. Now you might be thinking, well, wait a minute, what if it was a fraction like 3 over x? Well, that would be considered nonlinear because technically that would be 3 times x to the negative 1. Or even if it was absolute value, 3x. That's kind of the one, this is the one exception to the exponent of 1 rule, is when there's absolute value. Here it's on the denominator, so it's an exponent of negative 1. So just things to look at. Essentially what you want to look at is like, is x by itself in terms of like normal, then it's linear, and if not, it's going to be nonlinear. So the next thing to talk about is if something is rational or irrational. So rational means that it can be a fraction. And so then the definition of irrational with the prefix ir would mean can't be a fraction. Now, most things can be fractions. So for example, 1/2 can be a fraction because it is a fraction. 6.5 can be a fraction because that means 6 1/2. That's a fraction. Decimals, as long as they end, like 0.875 has an ending point. It doesn't go on forever. Or repeats. And that's what this bar means right here. So this decimal, even though it's going to go on forever, so this is going to mean 0.765656565, and so on, because it's repeating. I don't know how it emerges as a fraction, but I know that it can be, so therefore it's rational. Irrational numbers, numbers that can't be fractions, are going to be never-ending and never-repeating decimals. The most famous one is pi. And then any square roots of non-perfect squares. And so by perfect squares we mean like 4, because the square root of 4 is 2. Or 16, because the square root of 16 is 4. So any number that I can't just naturally take the square root of, that would be a never-ending, never-repeating decimal, and therefore it's irrational. The big one here to remember is that this repeating bar means that it is rational. It can be written as a fraction. The next thing to talk about is similar versus congruent. Now, it's also important to know that all transformations, like translations, dilations, rotations, and reflections, result at least in congruent or similar figures. Dilations are actually the only ones that are similar. So similar, I asked my daughter to read this, and she was able to sound it out. She said similar. And I asked her what similar meant, and she said same, but different. And then she had never heard of the word congruent, and so I told her that just meant same. And so for your purposes, similar is going to mean same shape, different size. Same but different. And congruent means exactly the same. They don't have to be in the same spot, but they just need to be the same size. So similar, they look the same, but they're different. Congruent, they're exactly the same. So this one, 2 different size triangles, they're going to be similar. Here, they're the exact same triangle. They're congruent. Similar triangles, same shape, different sizes. It's like we stretched it out. Here, same triangles but different sizes, similar. Orange and blue, exactly the same. One is just turned. And then this last one, orange and blue, it's a translation, same triangle. So those are congruent. So this next question was, what's the one-time fee in the chart below? So I can see here that for 1 hour it costs $60, for 2 hours it costs $80, 3 it costs $100, and 4 it costs $120. Now, one thing that's important to realize is if I divide like 120 by 4, I'm going to get 30, but then 80 divided by 2 is going to be 40. So that means that there's some hidden cost here, which is going to be that one-time fee. The one-time fee is what you're going to pay if you go for 0 hours. And so the easiest way to figure this out is to extend your table back and say, well, what would it have cost me for 0 hours? And I can see that every time I go backwards, it's going down by 20. And so if I go down by 20 one more time, because that will get me to 0, that means my hidden fee or my one-time fee is going to be $40. Now this problem is similar to last time, but I don't have a table to help me out. And so what I can do is I can think of it in two ways. One is to think of it as y equals mx plus b, and the other is the shortcut I'll show you in a second. So in this case, my cost is $20 per hour. That's my multiplier, that's my m. And they tell me I'm going for 6 hours. And then my cost is $150. It's like an add b. I don't know my one-time fee. 6 times 20 is, that's a 6, not a b. 6 times 20 is 120 plus b minus 120 from both sides, and I'll get a b of 30. So my one-time fee is $30. The other way I can think about this is, wait a minute, I'm going for 6 hours at $20 per hour. That should have been $120, but I actually paid $150. That means there's a difference of $30 that I paid, and that must have been my one-time fee. So there's two ways we can evaluate this one here. The first one I would say is, let's use common sense, and common sense to me is always PEMDAS. So first I would do what's in parentheses, and inside the parentheses I have 2 to the third power, which means to do 2 times 2 times 2. And so that would get me 8. Next in PEMDAS comes exponents, and I have an exponent here which is being attached to the 8, so I would square the 8, which means to do 8 times 8, which is 64. And then last but not least, I would do multiplication, and the thing that's being multiplied is 5 times 64. So 64 times 5, and I would do 5 times 4 is 20, carry the 2, and then 5 times 6 is 30, plus 2 is 32, for a final answer of 320. I personally think that's the best route to go, but if you wanted to apply the rules of exponents, what you could think of is, okay, 2 to the third is being raised to the second power, and so the shortcut would apply, AME. An exponent is being exponented, therefore I get to multiply. So that would mean 2 to the 6th, and then times 5. Now, if it helps, you could think of it as 5 times x to the third to the second. And if you saw it like this, you might think, oh yeah, the exponent is being exponented, and that would be x to the 6th. And so when we apply these shortcuts, the base does not change. Same thing here. When I apply this shortcut, the 2 doesn't change. Then I would do 2 to the 6th, which means to do 2 times 2 times 2 times 2 times 2 times 2, and that's going to come out to 64, and so I still have 5 times 64, which is 320.